Hello, class. Welcome back. Today is lecture 11. We are talking about the method of undetermined coefficients, which is a technique to solve a specific type of differential equation, as always. And so let's get started. So it is going to require that you understand what we did last time. So last time we solved, or we saw how to solve nth order super long word, linear homogeneous differential equations with constant coefficients. So things like this. So you solve using the characteristic equation and doing all that fun stuff. So this time we're going to get a little bit more complicated. So next, we're going to do it where it's no longer homogeneous. So what does that mean? That just means that instead of having 0 on the right, we're now able to have some other stuff there instead. But we're still going to limit ourselves a bit. So we'll see why in a second. So now we're doing equations of this form. So there's still constant coefficients. And now I can have another function of x on the right called g of x. Okay, so here's how we're going to solve these. So first step is actually that we need something called the complementary solution. And that is just the solution to the homogeneous version. So we call this y sub c for y complementary, I guess. So it sounds fancy, but this is just the solution, the general solution to the homogeneous version, which we learned how to do that last time. So you just make g of x be 0. So you just solve it like we did last time. And then that part of the solution is now called the complementary solution. But that's not the end of it. So next, we also need to get something called a particular solution. And that we call y subscript p. And that's basically what we learned how to do today. And that's what uses the method of undetermined coefficients. That's what will solve this. We'll get this piece for us. And then the general solution to the differential equation is yp plus yc. That'll be the end of these problems. Okay, so again, last time we learned how to get this. Oops, sorry. Did this last time. And this time we use undetermined coefficients technique in the title of the section. Okay, so instead of describing the process in general, it's best to see an example. But the idea is basically this. If g of x, the thing on the right, is nice, in quotes, we can guess yp. It's a very educated guess. And that's the basic idea for this technique. So what does nice mean? So for us, nice means something like this. Well, if I take a derivative of a polynomial, then it's going to turn into another polynomial. And if I take a derivative of an exponential, it'll turn into an exponential. If I take a derivative of a sine or a cosine, it'll turn into a sine or a cosine. So the basic idea is that the left side of this equation is a linear combination of whatever your solution is and its derivatives. So if you have a linear combination of things and they need to add up to g of x, then if g of x looks like a polynomial, for example, then we know that we need these things to be polynomials so that they can add up to a polynomial. That's the basic idea. Same thing with exponentials and sines and cosines. So we need the left side to add up. Polynomial, and that means like, oh, that means y better be a polynomial in the first place because I'm just adding it up with its derivatives. So if I wanted to add up to a polynomial, I better start off with a polynomial. That's the basic principle. Okay, but now let's see the principle in action with an example to see how it works. So we're gonna not worry about the complementary solution for now. We're just gonna find a particular solution using this technique. 2y double prime minus 7y prime plus 12y equals 4e to the 2x. So then this is called the method of undetermined coefficients. Okay, so the idea is like what I said above. So what we do is we look at g of x for e to the 2x. And we say, okay, so my solution that I'm going to guess, it better have an e to the 2x in it, because when I take derivatives of this thing and I do a linear combination of those derivatives, it's got to add up to this 4e to the 2x. But I just don't know, what I don't know is how many e to the 2x's I should have. So I call it a, e to the 2x. And so all I'm doing is I'm making a guess based on g of x. But I'm picking like a very general form of g of x is the idea. And hopefully I'll be able to figure out a, aka the name undetermined coefficients comes from doing this step. Then determine a by plugging it in. So I'm going to determine the coefficient a by plugging it in. Plugging it in where? It's the differential equation, of course, because then I'll know what a needs to be to solve it. All right, so I need to find its derivatives. So I can plug it in. And then I will just go ahead and plug it in. So I get 4a e 2x minus 7 times 2a e to the 2x plus 12 a e to the 2x. And then it equals 4e to the 2x. So now I can figure out a, sort of similar to what we did last time with the characteristic equation. In this situation, I can factor out an e to the 2x. I got 4a minus 14a plus 12a equals 4 e to the 2x. So the idea is now, in order for this to match, I need this many a's to add up to 4. So for a e to the 2x to be a solution, we must have that, well, what's 4a minus 14 plus 12? That adds up to 2a. So I must have that 2a has to be 4. So a equals 2. So my particular solution is yp equals 2e to the 2x. And that's it. And you can check by plugging it back in that it'll work, if you like. Okay, so then the general solution just comes from solving the homogeneous version. So now I just have to do that to finish the problem if I really want to solve it. So now this requires also solving this thing to get, and that'll get me yc. So if you end up doing it using the characteristic equation, I'm just going to save time since you're experts at that now. You should know exactly how to solve it. And so you can check, and this is what you'll get. So then the general solution. So then the general solution to the original, so this thing, is y equals yp plus yc. So that's going to be 2e to the 2x plus c1e to the 3x plus c2e to the 4x. And that's it. Okay, so again, this we did last time. So you should be experts at that. And then this is good. This is the new technique. And then adding them together gets you the general solution. All right. So it's actually better to get the complementary part first. So we're going to do that first from now on. So just to be clear, why is this a solution in general? Well, if I plug in yp plus yc into here, this will work in general, but I'll do it in this little example to get the idea. So if I plug that in, the reason it works, what was that, 12? Is because the derivative goes through addition nicely. So the second derivative of yp plus yc is just the second derivative of them added together. And then I can do the same thing on each piece. So I can distribute the 7 as well after taking the derivative. So this is why everything works in general, but just doing a specific example. And then I could regroup oops. I could put the particular parts together and the complementary parts together. And then what does this equal? Well, this was a particular solution. So what we showed is that that is what adds up to 4e to the 2x. And this is a solution to the homogeneous version. So this just equals 0. So yes, plugging in yp plus yc to the left side does get you this. Plugging in yp alone would also get you this, but because yc plugging in gets you 0, you get a whole bunch more solutions, which comes from adding them together. Okay, so that's the general idea there. But let's get some more practice with the with the process. Okay, so let's do this. Solve this thing. So just to keep things simple, I'll make the left side be the same and I'll just change the right side. And so here's why we're going to see why you should get YC first. We'll see what goes on. So we're going to get the complementary solution. The left side is the same as last time. So it's just going to be the same thing. If you change the right side to 0, you're still going to get C1 e to the 3x plus C2 e to the 4x. So that's the same as last time. So now we're going to get YP. So our first guess is going to be, well, I look at the g of x and I say, okay, I need e to the 4x, but I don't know how many. Because a linear combination of its derivatives to add up to 5e to the 4x, it can only happen if I start off with some amount of e to the 4x's. But this is not going to actually work this time. And why not? Well, all we have to do is notice that our first guess is actually already included in the complementary solution. So if I do this business of okay, here's my guess, and then I plug it in, and I check, and I like match the coefficients again. Oops, let me just go like this. It's not going to work because what is this just going to add up to? This is just going to add up to 0. Because it's part of the complementary solution, which is the solution to the homogeneous version. And the point of the complementary solution is that if I plugging this in gets you 0. And it doesn't get you any e to the 4x's. So this guess is not going to work because it'll just end up being 0 when I plug it in. So instead, we have to fix it, but it's easy to fix, luckily. So then, to fix this, we try a different guess that we get by just multiplying our first guess by x. So instead of e to the 4x, I do x e to the 4x. And then I go and I look and I see that that is not in here. So it's not just going to go away and become 0. It is going to work though. So it's a very sneaky trick. So all I have to do is take my guess and multiply it by x, and then it'll magically work. So I'm not going to go through the details of why that's not working. It's a bit more than is necessary, but you can try to figure out why it's working. Luckily, it does work, and that's all we need to know. So if you plug it in and you solve for a, you will get a particular solution, and that's what we need. Okay, so now we're going to do the same trick as before. So that means I need my first derivative, which now I have to use the product rule, slightly annoying. So the derivative of ax is a, keep the second one the same, add, keep ax there, take the derivative of 4e to the 4x, which gets you that. So this will be 4ax e to the 4x. I also need the second derivative. So you can see these problems will get very big very quickly. So the derivative of this is 4a e to the 4x plus derivative of 4ax is 4a, keep the second part the same, add, keep 4ax the same, derivative of e to the 4x is 4e to the 4x. So we end up with 8a e to the 4x plus 16ax e to the 4x. So now we got to plug these guys in, these three in, to the differential equation and solve for a, and it gets very big very quickly. Okay, so again, same differential equation. So yp, I'm plugging it in into this thing. What was that? It was 5e to the 4x. So what is this? Okay, well, yp double prime is 8a e to the 4x plus 16ax e to the 4x minus 12 times yp prime is a e to the 4x plus 4ax e to the 4x, and then plus 7 of these ax e to the 4x's equals 5e to the 4x. And then we are just going to combine like terms. So, so I want to get all my e to the x's together. So there's 8a of them there, minus 12a of them here, for example. Oh, wait. Should there have been a... Oh, I switched the 12 and the 7, didn't I? Ah, crap. How long ago did I do that? Oh, just right here. Okay, sorry. So this is a minus 7 plus 12. Okay, so let's fix this. Okay, and then this is a 12. Okay, so let's see. So now I have 8 A's minus 7 A's of e to the 4x's. And now I have 16 A's. What's 7 times 4? 28 minus 28 A's plus 12 A's of the x e to the 4x's. So there I've combined these ones together. After distributing the 7. And that should all add up to 5e to the 4x. So this is really a lot of algebra. It's just more algebra. So then we just match terms. So how many e to the 4x's are there on each side? Well, there's 1a, this is just a. So there's a on the left and there's 5 on the right. So a has to be 5. How many x e to the 4x's are there? There's 0 on the right. There better be 0 on the left for it to make sense. And that does add up to 0. So we're okay. But the point is that this solves for a for us. So yp is now 5x e to the 4x. So then what is yc plus yp, which is a general solution? It's the particular one, which we just got, plus the complementary one that we already had a long time ago. And that's it. Okay, so quite a lot of algebra. So this technique also can be expanded into other types of functions on the right. So I said at the beginning that the functions have to be nice. And exponentials are nice because when you take derivatives of exponentials, you get more exponentials. Another type of nice function is a polynomial, which is just powers of x, because when you take derivatives of powers of x, the powers go down and you get a new polynomial. So this technique will also work here. Okay, so this guy is polynomial. In particular, it's a quadratic. So the technique will work again. Okay, so in a second, we'll say what to guess, but first let's get the complementary solution. So let's see very quickly, lambda squared minus lambda minus 2 equals 0. Lambda minus 2, lambda plus 1 equals 0. So that tells me that the complementary solution is c1 e to the 2x plus c2 e to the negative x, right? From last time. Okay, so now our guess. Well, let's see. When I take the derivative of a quadratic, I don't just get a quadratic. So I'm not just going to guess this. In fact, what I'll get is lower powers of x. So I have to figure out how many lower powers of x might also be in here. So I have to go all the way down to no powers of x from the highest. So that's because this is, you can think of it as like the general form of a quadratic, but it's because the derivatives of x squared give you lower powers of x. Okay, so this is going to be our guess. And again, we have to see, like, does this have anything in common with our complementary solution? No. So we can proceed. We don't have to fix our guess like we did last time. We can just plug it in. Okay, so then plug it in. But it's a bit more annoying because now I have 3 things I have to determine. Instead of just one, I have to determine A, B, and C. So it's a lot longer. Okay, so to plug it in, I gotta get the derivatives, which would be 2ax plus b, and second derivative would just be 2a. Okay, so I'm gonna plug these into the differential equation up here and match the coefficients. So I get 2a minus 2ax plus b plus, it was a plus, right? Oh no, it was another minus, minus 2 times yp, ax squared plus bx plus c. And that needs to equal 4x squared. So I'm now going to combine like terms and match the coefficients again. So let's see, what are the like terms? So like the things with no x's, I should put together. So I get 2a minus b plus c. The things with 1 x's, I should put together, just 1 power of x. So I have a minus 2a plus b x, and then the things with x squareds, there's only one of them, negative 2a x squared. So now I know what a should be, and I can also figure out b and c, because the idea is how many x squareds are there on the right? There's 4. That means I need this to equal 4. So that tells me that negative 2a equals 4. That's how many x squareds I need. A equals negative 2. And then this tells me that, well, there's 0 x's on the right, so negative 2a plus b better add up to 0. But now I already know a, so I can figure out b. And then this better add up to 0 because there's 0, no x terms on the right too. And now that I know a and b, I can figure out c. So negative 4 plus 4 plus c equals, that doesn't sound right. Sorry. Maybe I made an algebra mistake. I guess C could be 0. In my notes, I did something else on accident. Oh, it is. There's a 2C. 2 times C. That's what it is. Oh, wait, that'll still be 0, though. What happened? Sorry, let me check my work. Bad at. Oh. This was also a 2B. Right here. Dang it. Because I forgot to multiply that 2 in. Okay. Okay, I can do this. So now that's going to change that a little bit. So I'm going to fix B. So B. Okay, so A was good. So then this is still 4 minus 2B equals 0. So B will be 2. Add the 2B, divide by 2, B equals 2. Okay, good. So now this becomes -4. That's good. Minus B, so minus 2 plus 2C equals 0. So that gives me what I want, I think. So this should be -2, add it to the right. Oh, dang it, so many algebra mistakes. Minus B, so this is minus 2. There we go. Okay, so now I have 2C equals 6. C equals 3. Oh, God, did I mess up again? Yes, I did. There should be a minus 2C. Sorry. Because this is a minus, of course. So this is a -3. All right, now we got it. Okay, my notes are correct. All right, so now what's YP? So now I just plug A, B, and C back in. -2x squared because of A plus B is 2x minus 3. So then what's Y? My final general solution. It's the particular solution plus the complementary solution, which we did a long time ago. And that's it. Okay, so that's that. So next, the last type of one we can do is if the right side is a sine or a cosine. Again, because the derivative of sine is cosine and the derivative of cosine is sine, they flip back and forth. When you plug in its derivatives, you can start with a sine cosine combination and figure out the coefficients that make it add up to just the right side. Okay, sorry, let me change this to a 2x. So you can also do different multiples of x inside as well. So the process will be the same. The left side is the same as the previous problem, so that the complementary solution will be the same as last time. But our guess for YP will now be, well, I don't know how many of these I need, but because sine and cosine flip back and forth when you take derivatives, the left side could have a bunch of cosines being added up together and canceling out to get no cosines, but I still have to include them in here to see if that happens. So this is going to be the guess for if you have a sine or a cosine. And notice that this number needs to match, so it's the same type of sine. But in any case, that's your guess. And then you're going to have to do the same thing. So you're going to take derivatives. And plug them all back in. So I don't want to do it. It'll take way too long. But this is how you start it. Plug these 3 back in. match coefficients to figure out A and B. Okay. So it'll take a while, but it can be done. So instead of that, I would like to give you these other principles to think about. So these next ones, we're not going to ever do problems as big as these next ones, but it's a good idea to understand what's going on. Okay, so then next, can also guess yp if g of x is any linear combination of the things we just did: polynomials, exponentials, or sines and cosines. And the reason is because if you take derivatives of linear combinations of these, so if you have something like this, e to the 3x, x squared plus 2x minus 1 times like sine of x. If you take derivatives of something like this, it'll take forever, but the derivatives will still be linear combinations of the same things. So what that means is we can still guess. We're not going to do this. This would be awful. But what we can do is we can combine our guessing abilities. So we can say, well, I see an e to the 3x. So my initial y solution should have one of those in there. Because when I take derivatives of it, I'll have more of them. I see a square term. So I should have some of those. So when I take its derivatives, they'll still be there. And then I see a sine. So I need more letters. Whoops, there should be a D. So my initial thing could have sines and cosines in it too. So that when I take the linear combination of its derivatives, I end up with this big old mess. I need to start off with some amount of each of them. So your initial guess would be something like this, but you could actually distribute and reorganize, but we're not going to worry about that too much. You can distribute and rename the constants so you have less constants to worry about. But we're not going to worry about that. The point is that to think about why this kind of guess would work if you had a differential equation with the right side looking like this. And it's just because taking derivatives of things like this results in more functions of the same kind. Okay. So then when will this technique not work for the same reason? So this undetermined coefficients technique will not work. For example, if the right side was ln of x, because the derivative of ln of x is 1 over x. And so the idea is that it's too different. It's a change of type of function. So the other functions are nice because when you take their derivatives, you get the same type of thing. But the derivative of a log changes the type completely. So this technique will not work for things like this, just to be clear. And then the last thing I want to say is something called the superposition principle. So the idea is that earlier we solved these two differential equations. Y double prime minus 7y prime plus 12y equals 4e to the 2x, and y double prime minus 7y prime plus 12y equals 5e to the 4x. So we already solved both of these. So notice that the left side is the same. Well, the superposition principle tells us that the particular solution to, if I add the right sides up, so if I keep the left side exactly the same, but I take these and add them together, is it's just the YP's added together. And both of these up here. And the superposition works like this. Superposition principle works like this, but in more generality. So I'm just giving you a specific example. So if you look back in your notes, we already figured out YP for both of these. So for this one, YP was 2e to the 2x. Yes. And YP for this one was 5x e to the 4x, if I look back and see, yes. So then YP for this differential equation is going to be, if I work it all out the way I did before, I will still get the same answer. It'll just end up being this. And you can do it the long way. So you can get it from doing something like, okay, well, I should guess, because my right side has 4e to the 2x, I should guess ae to the 2x. And because my right side also has a e to the 4x, I should guess something e to the 4x. But then because this one matches the complementary solution, I multiply it by x. So this would just be like my first guess. But then I would fix it by fixing that piece. So if you did this, you would end up with a equals 2 and b equals 5. If you plug that back in with its derivatives to the differential equation, and solved for a and b, you would get the same thing as this. Okay, so then of course, the general solution is that still works the same too. Oops. C1, so we solved this one earlier, e to the 3x plus c2 e to the 4x. That would be the general solution. Okay, but this is called the superposition principle. And the idea really comes from, again, the fact that derivatives go through addition. And that's really what makes this work. So you can think about it more if you like. You may use it a couple times, but not too often. But it's still interesting. Okay, so that's it for today. The main thing is to be able to do the undetermined coefficients technique for the things that we did earlier. So don't get too bogged down. There's a bunch of stuff, but you should be able to do ones like this, ones like this, and ones like this. where you have to fix it by multiplying by x, or ones where you don't have to multiply by x either. It's fine. It's also good to know. But don't worry so much about when we combine guesses like this. Just know that it's possible. Okay, so that's it. See you next time.